Hi, and welcome back to Codex. Our speaker today is Professor Hartmut Führ from RWTH Aachen University. Professor Führ earned his doctorate at TU Munich in 1998 and his habilitation in 2003, also at Munich. He held positions at Université de Provence Marseille and GSF Research Center for Environment and Health before becoming an associate professor at Aachen in 2007, where he has also served as department head. Professor Führ is a champion of abstract harmonic analysis and is responsible for fundamental research in co-orbit theory, continuous wavelet transforms, and their applications. We are pleased to have him with us today to discuss his recent work on frames of translates. Please take it away, Professor Führ.
Thank you very much, first of all, for the kind invitation to give a talk, and secondly, also for the very kind introduction to this talk. So let's get started. What I've seen so far is that I'm talking to a group of experts here, which will allow me to be a bit quick maybe at some points, but I do want to get a couple of things across. So this is a talk about frames of translates in fairly general settings, and about an intuition that I've always had somewhere in the back of my mind when I looked at questions like this, and which has to do with essentially the way that these things work out over the reals. And well, and this is essentially about whether this intuition actually holds up in the more general settings or not. And the answers are going to be varied, I would say. So sometimes the bandwidth intuition is quite valid and sometimes it's not. And it's also, I should say, it's an intuition, so it's not really strict. Those are not really strict results that give an entirely sharp image. Okay, so much for the prelude. So let's get going. I'm planning to talk about 4 sections. So the first one is very short and essentially just a fixed notation. I will talk about what I understand by frames of translates. Part 2 is essentially about trying to develop what I mean by bandwidth intuition for the underlying group being the reals. And then we will look at 2 slightly different settings. So essentially, frames of translates, the question there is you have a locally compact group and you ask yourself the question, which spaces have frames that you obtain by fixing a particular function and shifting it using the group action on functions on the group. There are 2 variations to this. So initially this question was mostly looked at over locally compact abelian groups, or more precisely over reals or maybe Rn, and then different ways of looking at this problem were developed later, and different versions of this. One of them is where you what section 3 is about. So this is essentially the game that you're playing there. Is you don't have you have a single group, and then you have subgroups of that single group, and you allow essentially you're looking at frames that are generated by having each subgroup act on its generator, and then taking the union of that system. Part 4 is essentially looking at non-abelian groups, and I'm reporting on joint work here. Section 3 is about results obtained with Jakob Lemvik, and section 4 is about results obtained with Vignon-Husser. Right. So let's get started with the actual mathematics. Throughout this talk, G is a second countable locally compact group. Most of the times it will be abelian, and if you're just thinking if your main locally compact group is the reals or RD, that's fine for most of the parts of the talk. On each such group, there's Haar measure, left invariant, Radon measure, which is unique essentially, and there's the associated space L2 of G that's taken with reference to mu G. Right, and now what we're looking at are left invariant subspaces, closed left invariant subspaces H subspace of that L2 space G. And a frame of translates for such a space is given essentially by picking a single function G from the subspace and taking and shifting this by from the left by suitable elements from chosen set gamma. That gives you a system of vectors, which in our setting will be countable. And if taking scalar products with that set essentially gives you back the L2 norm of the of a function up to constants A and B, that's a frame, as I should say most of the people present know perfectly well. The frame is called tight. We will mostly be concerned with tight frames, but well, okay. In section 3, mostly will be about tight frames. Gamma will be called the translation set. We call the translation set regular if it's actually a subgroup. Okay, and the questions you can ask yourself, I mean, there are many questions you can ask yourself in that context, but those are questions that definitely arise if you start thinking about this. Which frames, which left invariant closed subspaces actually have frames of translates? Then another question that's related to that to some extent is, suppose you have such a subspace and you know you have a frame of translates. Is there some requirement on the set gamma that the set gamma has to fulfill that is somehow induced by the property that just by shifts from gamma you get a frame of H? This is kind of roundabout way of leading up to what will be density later on in the talk, but let's leave it there for the second. And then finally, a question that will mostly be a corollary of the second question is, can we pick the L2 space of the group itself? And does that have a frame of translates? Okay. And what I will do now is essentially look at these questions for one particular locally compact abelian group, namely the reals, and then go from there. So first of all, here's a list of references that, in my view, are relevant and pertinent to this question. And I want to point out and also want to make an apology at this point to anyone who has worked on the subject and is not listed here. The main point of this slide is to point out that this is that there's a diversity of influences and a diversity of contexts in which one can look at this question. So just let's go through the history. I think all originates with sampling. The Shannon sampling theorem is a first case of actually an orthonormal basis of translates for a particular space of for a particular subspace of L2 of R. Then irregular versions of that were considered by Duffin and Schaefer. Kluvanek generalized this to locally compact abelian groups. Then there are, if you look at, again, irregular sampling, then there's the work of Landau. Then again, this is highly subjective, and I'm mostly looking here at influences, at sources that influenced me along the way. Feichting and Gröchenik had a substantial body of work that was considered with questions of that type and with discretization, actually in a much larger context, namely co-orbit theory. Yes, and okay, here are a couple of names that need to be mentioned: Chris Heil, Guido Weiss, Ole Christensen, I think. Okay, and up to this, I should probably say that a lot of this takes place more or less exclusively on the reals, maybe with the exception of Kluvanek, and then more recently, other areas of interest emerged, like to look at this question, say, on other types of groups, say finite groups, to mention Waldron and his work. Nilpotent Lie groups. Angelika Höfler is a PhD student of Charlie Gröchenik, and the reason she's here is because, or I'm putting her here because she actually worked on density results that were obviously inspired by her supervisor Charlie Gröchenik. But this is kind of for me, this is is one of the sources that's always kind of in the back of my mind. Then there's more recent work also on nilpotent and solvable Lie group by different subsets of Bradley, Curry, Azita Mayeli, and Vignon-Usa. There's work by Joey Iverson on left actions of abelian or compact subgroups of Lie groups, and for sure the list doesn't end here. But okay, so as I said, the main purpose of this slide is to remind ourselves that there's quite a variety of contexts where you can ask yourself this question, or questions like that, and essentially what I would like to point out in the following slides is that one way of trying to understand these things are in terms of density, and sometimes density goes a long way, and sometimes, as we'll see, it doesn't go anywhere at all. So, but here I'm already getting ahead of myself. Okay, so now I want to look at these questions over the reals. So the first theorem has two typos in it. The first one is I'm looking at closed invariant subspaces of H that are subspaces of the L2 space of the reals, and here's an F missing. So this is, first of all, if you recall, I was looking at invariant closed subspaces of the L2 space, and the question whether these had frames of translates. And so the initial thing is to understand what are the actual closed invariant subspaces, whether they have frames or not, and the ones that, and all closed invariant subspaces are of the form H omega, where omega you can think of essentially of omega being something like the spectrum of the L2 space of the subspace. So each closed invariant subspace comes with its Borel set, and this Borel set is essentially unique up to sets of measure 0. And if you, okay, now you can ask yourself the question, given H closed invariant subspace, so I know that it has a corresponding Borel set. Does the Borel set tell me anything about the question about the existence of frames of translates? And the answer is will be yes. So in order to understand this, we need a notion that will be particularly pertinent for the regular case. So remember, regular translation sets are subgroups. So if I have and what I need for that is essentially the notion of a tile and the notion of a subtile. So a tile is a tile. If you are given a lattice, a tile is essentially a measurable set that if you take shifts of this set under the lattice, you get a disjoint union that gives you back the full set of reals. So here everything needs to be taken up to sets of measure 0. So the right-hand side could be R minus a set of measure 0. That doesn't matter. And the disjointness that's indicated here by the dot above the union sign is again up to sets of measure 0. Well, because you can always make it fully compliant by changing omega by a set of measure 0. And a subtile is essentially a measurable subset of a tile. So a subtile is defined by just by the definition that shifts under gamma, non-zero shifts under gamma of the set omega are disjoint, again up to set of measure 0. Okay, and here's a first result that relates essentially the question of existence of frames to a property of omega. So if H equals H omega, then there exists a frame omega frame generator for the lattice alpha z. So here I'm looking at the reals again, and alpha z, all lattices are of the form alpha z for some positive alpha. And the existence of a frame generator can be decided exactly by looking, comparing alpha, relating alpha and omega, namely there exists a frame generator for alpha z if and only if omega is an alpha inverse subtile. So in particular, so if you think of omega as usual as being an interval, this tells you that in order for the existence of a frame generator for alpha z, you need that alpha inverse has to be longer than the length of omega. Okay, and to already take some language that we will use on the later slides, alpha inverse is essentially the density of the lattice alpha z. So what this says is the density of the lattice should be larger than the length of omega. At least if omega is an interval. Okay, and I've attributed this theorem to Kluvanek. Kluvanek showed essentially the case of tiles and replaced frame generators by orthonormal basis generators, but the argument essentially works the same. Okay, and now this is already the full answer to some extent for regular sets of translations. If you want to have an answer for irregular sets of translations, it gets more involved. Here you need the upper Berling density of gamma, which is essentially obtained by taking an interval, shifting it along the real axis, and counting how many elements of gamma are in this interval, depending on x. The sup of that gives you a value depending on r, and if r, then you take the Lehm sup as the length of the interval grows larger and larger. That's called the upper Berling density. For lattices, that's really not. That's kind of an overkill to define it like that. But for lattices, it turns out that the upper Berling density is again alpha inverse, the density I've used on the previous one. What you get using this Berling density is the following result due to Landau. Note that it's only with reference to a particular frame generator here, but it gives a very precise condition. Lx gamma is a frame, then the Berling density has to be greater or equal than r. And actually, you can replace r here by measurable sets and get comparable results. Okay, and okay, so in a sense, this is a generalization, but of what we had for regular sets of translates, but it's not really comparable. But what the two criteria have in common, obviously, is that there is a relationship, a necessary density that the set of translates has to fulfill. Okay, why is there any benefit in looking at irregular sets versus regular sets? The answer is yes. This is actually quite recent result, as far as I know, and it's not really a result. It's just pick something, just uses a result from someone else. It's a simple observation. So remember that the necessary condition for the existence of an alpha z generator for the space H omega is that omega is an alpha inverse z subtile. Now it's possible to choose sets omega that are of positive measure that are subtiles that are not subtiles with respect to any alpha. So whatever alpha however small you pick alpha, you will not, if you put, for example, omega to be open, dense, and a finite measure, so just a union of open balls around the rationals that are sufficiently small, then any shift of omega will intersect omega in another open set, because you have two dense open sets there. They have to intersect in an open set. That's of positive measure, so that set is not an alpha inverse Z subtile. So the space H omega does not have a set of regular translates as a frame. But it turns out it does have an irregular set of translates as a frame. And to see that, essentially what you use is the fact that it has a continuous frame of translates. For that, you can just use the function g hat to be the characteristic function of omega. And if you take all the shifts, so now you're taking the full set of all real shifts of that, then you get a continuous frame of translates, which means essentially that convolution by this function g acts as the identity on h omega. So that's a continuous frame of translates, and there's a recent, very remarkable and very powerful theorem by Freeman and Spiegel, which I think goes back to the solution of the Feichtinger conjecture, that tells us that continuous frames of consisting of vectors of bounded norms can be discretized. So there exists some set of translations gamma prime, such that picking this particular frame generator combined with this set gamma prime of translates is in fact a discrete set of gamma of the space h omega. So this space h omega that does not have a regular set of frame of translates has an irregular frame of translates. So irregularity actually buys you additional power. Okay, so given that, you could ask yourself, is it possible? Okay, now you can ask yourself the question: is it possible? We already know that from the previous results, if you take omega to equal the reals, there is no way by the same argument that we've run here for omega, the way it's given in the first example, there's no way of actually getting a frame of translates for L2 of R. So the question then becomes, there's no regular frame of translates at least. Is there an irregular one? By a result by Christensen, Deng and Tai from 1999, the answer is no. L2R does not admit a frame of translates, and I think this kind of fits well with the density intuition that I'm trying to build up here in the first section of the talk, simply because if you say density is related to the measure of the support or the length of the support in Fourier domain, so it's the length of a set omega, the length of omega equals R, which corresponds to this full set L2 of R, that's infinity, so you need density infinity. And if you look at the proof of Christensen, Deng and Tai, they essentially prove that. So they look at the upper Berling density and they show that a frame would have to have infinite density to get the lower bound, frame bound, and finite density to get the upper frame bound, so such a thing doesn't exist. Okay, and this is kind of what I want to keep as a reference for the remainder of the talk. So again, here we looked at G equals R, so this is another typo. It should be H and L2 of R, which left invariant subspaces, which just means shift invariant subspaces of L2 of R, actually have a frame of translates. And the answer is, if you want if you allow any irregular set of translates, it's just those that correspond to finite measure spectrum. And we also know that the answer for lattices is actually more strict, because then you have that the density of the lattice has something to do. So the then you have the subtiling condition. And now, given any h equals h omega, what structural requirements on the translation sets do we get? And here I want to retain for the remainder of the talk the main intuition that the density should be bigger than the bandwidth, and the bandwidth can be either interpreted as the length of the spectrum or the measure of the spectrum. But in any case, it is some condition derived from the spectrum, and it translates to a necessary density condition for gamma. And by this intuition, it's you're perfectly fine to conclude that omega, it's for L2 of R itself, there's no frame of translates, simply because you would need infinite density. Okay, and what I want to do for the remainder of the talk, I want to go to two different settings: locally compact abelian groups and non-abelian locally compact groups, and want to see what becomes of this intuition. Okay, and the first will be generalized shift invariant systems in locally compact Beerian groups. This is work with Jakob Lemwig. So the system, what we're looking at here is a more generalized setting in a sense, because instead of having a single lattice, so we will only focus on regular lattices, but instead of having a single lattices, we have a family of lattices. And the question we ask, and now the question becomes, is it, so for each of this set of lattices, what we're allowed to do is for each lattice choose a different L2 function, shift that by elements from the lattice, and take the union of all those families. So for each lattice, gamma j, you're allowed to choose a generator gj. That gives you, again, a countable system of elements in L2, and you want to know whether this, you want to know whether you can get a frame this way. And we will focus on tight frames, so we will only look at frames where the upper and the lower frame bound are identical. And essentially what we would like to understand is which lattice systems allow to conclude that there are tight frame generators. Are there lattice systems, and a very basic question that going into this project, I had no idea whether this was true. So suppose you have any infinite system of lattices. Is it possible to get tight frame generators for this system? And what are the criteria that help me decide this? And then of course the question raised by the first sections was, does this have anything to do with bandwidth? Okay, so in order to do this, so we're doing this over locally compact Beerian groups. We need some basic facts from this theory. I think I can be brief here. So we use Fourier analysis on locally compact Beerian groups. There's a character group. That's just a group of all continuous homomorphisms into the torus. It is topologized in a proper way. The Fourier transform of functions in L1 of G is obtained by integrating against characters. This gives us, in fact, a unitary map between the L2 spaces. For a dual lattice, for a lattice gamma in the group G, there's a corresponding dual lattice in G hat, which in fact is a lattice. It's also a co-compact discrete subgroup that's characterized by the requirement that the lattice, that chi vanishes on the lattice. And essentially, this will correspond to alpha inverse Z in the examples that we had over the reals. And we also have a general characterization of closed invariant subspaces of L2 of G. Here's the same typo. So F should be, it's the set of all F in L2 of Gs that are supported. So here should be an F hat that are supported in a suitable measurable set. So there's again a one-to-one correspondence between closed invariant subspaces of L2 of G and the Borel set. So once again, so this time we're just interested in finding frames of translates for all frames of, we're interested in frames of this time arising from generalized shift invariant systems. So we have a family of lattices, and for each lattice we can essentially pick a different generator, and we look at the system we get this way. But obviously the first thing to understand is how much can you do with one lattice. This we will essentially use to build up our bandwidth intuition for general locally compact Beerian groups and GSI systems in there. So what we will retain also from the Euclidean set is the terms tile and subtile. Again, a tile with respect to a lattice is something that gives a tiling of the full group by shifts from gamma, and a subtile is a measurable subset of that. The density of a lattice will be now defined as the inverse of the measure of a subtile. It's independent of the choice of subtile. And what you can show is that the lattice, the densities of the lattice and the dual lattice are related by this formula. So they're inversely proportional. And this is already something we saw in dimension 1 over the reals. And then the argument using by Klovanec is again valid here in the general locally compact abelian setup. So if you have a set H that has a spectrum omega, then there exists a frame generator for gamma if and only if omega is a subtile with respect to the dual lattice. And in particular, you get the same density condition for the lattice that we got over the reals. Okay, but this is a single lattice. Okay, what can you do with this? So here's one obvious way you can think of exploiting this. Okay, now I have a system of lattices, and what I then do is, if I want to have a frame of L2 of G, that I get by letting the system of lattices act on different vectors, is I decompose L2 of G into subspaces H omega. That correspond to a covering of the frequencies, and then for each omega, I have a lattice that's responsible just for that. And that's essentially the basic idea behind this simple-minded construction. So this is a simple way of constructing general shift invariant frame generators for certain sets of lattices. So first of all, we note the following, that just in order to have a complete system, so again, we start out by the gamma j, and then for each gamma j, we choose generator gj. And just in order to have a complete set of translates in the L2 space, the minimal requirement is that if you add up the Fourier transformed squares of the generators in Fourier domain, then this sum is almost nowhere vanishing. And the argument is pretty simple. Suppose this were not true, then any function that lives where this sum vanishes will be orthogonal to all the shifts of all the GJs. So the system cannot be total. Okay. Now the basic idea in order to generate a shift invariant frame is to use for the generators, just use indicator functions in Fourier domain. You make them gamma j subtiles, so this gives you a tight frame of H gamma j. Okay, then I mean, okay, we're still here in we will have to pay a price for this, but assume that we can cover the full set of frequencies by such subtiles omega j. We can actually make this union disjoint by cutting away subsets of gamma omega j's. That doesn't change the subtype condition. So I can make the union disjoint. Then I decompose L2 of G into an orthogonal sum of the corresponding spaces, and each tight frame here is actually has a tight frame, and if I take the union of those tight frames, I get a tight frame of all of it. Okay, this is I'm not saying this is a particularly subtle construction, but it works under the condition that such a covering is available. If you actually manage to have not just subtiles but tiles, and if those tiles are essentially disjoint, you actually end up with an orthonormal basis by proper normalization. Okay, and obviously this can only work. This works if you get if you can cover G hat by gamma j hat subtiles omega j. And we note that you can make this, you can derive a quantitative criterion for this to work, namely the densities, which happen to be which happen to correspond, which have to be larger than the measures of the omega j's. the densities of the lattices have to add up to the full Haar measure of the dual group. And okay, and the densities are essentially the bandwidths. So if I start with gamma j, then if I look at gamma j, the Kluvanek theorem tells me there's a certain bandwidth that gamma j can cover that essentially corresponds to the Haar measure of the corresponding frequency tile, and this is and I know that they have to add up to the full measure of the full group in order to work. Okay, and I'm sure everyone in the room has looked at constructions like this. This is not particularly deep. Okay, and now I will exhibit, and now things will change a bit, because now I will show that for certain lattice systems, this is actually essentially the only way this can work. So here I need a condition on the lattices that will actually apply to the dual lattices later. So I'm looking at a system of lattices, a system of subgroups, and those are not just disjoint; those are essentially disjoint up to generation. So what I mean by that is you have whenever you have a finite family of elements in where each xj comes from a lattice gamma j, and they add up to 0 in G, this can only happen if already all of the summands are trivial. So this in particular requires that gamma j and gamma j prime, the intersection of gamma j and gamma j prime is only 0, but it's a stronger condition than that. So now here's a theorem where this which gives a setting where this bandwidth intuition is in fact sharp. Suppose I have a lattice system such that the dual lattices are independent. Then I can show that there exists a tight frame set of generators only if and only if there exists a family covering of subtiles. So then sufficient condition from this very simple minor construction on the previous slide is also necessary. In particular, the densities have to add up to the full measure of the dual group. In particular, if G is non-discrete, this means that the bandwidth has to be infinite. Okay, so since I'm already a little late in the game, I have to skip the proof, unfortunately, although it's actually quite nice. Again, it's under a very strong condition, but it allows to exhibit a large class of systems where the intuition that we build up here, and that is admittedly very naive, is in fact the only way essentially of guaranteeing the existence of tight frame generators. So it's the proof builds on previous work by Jakob Lemwig and uses almost periodic functions. But I want for time, because of I feel my time is getting close already, and I want to have enough time for the non-Libyan case too. Let me show you a few consequences. So remember that one of the questions I was asking myself was, given any infinite set of lattices, is it possible? Do they necessarily have tight frame generators or not? And here is an example. Here are two examples: one over the R2 and one over the integers, where this is not the case. So what I'm doing here is essentially I start out with a set of lattices that I get by diagonally dilating Z2. So I dilate them by powers of C in one direction and inverse powers by C in the other direction. So each of these lattices has density 1. So their densities add up to infinity, which is the full measure of the dual group. But you can actually show that there does not exist a covering by subtiles. So we do know, we can conclude, because we know the lattices are in fact have independent dual lattices, because what I choose is not just any power, not just any C, but I use a transcendental number C. Then I can show that these lattices are actually have independent dual lattices, and then I know that the subtiling condition from the previous slide is actually sharp, and I can show that that subtiles don't exist. So this is an example where I have infinite bandwidth, but there does not exist a covering by subtiles, and there does not exist a family of tight frame generators. There's also an example over the integer numbers. So pick any injective family of prime integers that have whose inverse add up to a value less than 1. And you take the lattices in the integers that are just multiples of Cj. And you can then show, using the previous results, that there's no tight frame generators for these guys available. Okay, so this is a class of families of lattices where you can show that the density criterion and the bandwidth idea actually holds up, because you only get lattices if you get a dual subtiling. And now here's a class where the bandwidth intuition completely blows up in our faces. And it's the following theorem. So now we're looking at something like a complete opposite. We're looking at a sequence of strictly increasing lattices, of strictly decreasing lattices, gamma naught, gamma 1, and so on. So you can think of Z, 2Z, 2 to 4Z containing 8Z, and so on and so forth. So whenever you have that, you can define an orthonormal basis corresponding to this strictly decreasing set of lattices. So far you can say, so what's the problem? The problem arises when you actually compute the associated density and the associated bandwidth that corresponds to this sequence, because this bandwidth, this sequence actually has finite bandwidth. For the simple reason that's shown at the bottom of the slide. If you have a strictly decreasing set of lattices, the density decreases at least by a factor of 1/2 from each for each step you take. So if you add up all the densities, you end up with something finite. You end up with you can estimate this against a geometric sum. And if you truncate this sequence, the same argument still applies, and you actually get up. You can end up with arbitrarily small bandwidth. So this is an example where the bandwidth intuition completely fails you, because you get systems that have arbitrarily small bandwidths. So in particular, you have no chance of covering the duals by subtiles. Yet there exists an not just a tight frame, but an orthonormal basis associated to this family of lattices. Okay, so this shows you that there are conditions that you can impose on the family of lattices where the bandwidth condition essentially works as you would expect it, and there are other setups where it doesn't work at all. And again, I need to skip the proofs, unfortunately, because of time restrictions. There are a couple of open questions here. For example, just for finite groups, if you reformulate the bandwidth condition there, then essentially what it says is, if you have a finite Debian group and finitely many subgroups of that group, and then the bandwidth condition essentially boils down to just the requirement that the cardinalities of the subgroups add up to something bigger than the cardinality of the group. And so far as I know, the question whether there exist generators, let alone tight frame generators for this system, is not answered. And the question also becomes different if you look at frame generators instead of tight frame generators. Okay, so to somewhat summarize this, if you move to systems of lattices where you're allowed to choose a different generator for each, it very much depends on the structure that's somehow inherent in the system of lattices, how the bandwidth condition holds up. And now I want to turn to non-abelian groups, and I want to show a couple of examples that tell us that the non-abelian world, as you may have expected, is completely different than the abelian case. So now we're in the second countable locally compact setting. The group does not have to be abelian. And we only want to look at one question here. I just want to look at the question, is there a set gamma in G and a generator G in L2 of G such that the set that I get by acting on G by elements of gamma from the left is a frame for L2 of G. And obviously, if G is discrete, you can just pick the Kronecker delta at the neutral element and get an orthonormal basis by letting the full group act on it. That's the boring case. The non-boring case is the non-discrete case. Are there non-discrete groups which have these frames of translates? Okay, and in order to answer this, we need a definition that's related to density. It's essentially the requirement that that a set has finite density. So a set is called relatively separated with respect to the left structure, I should say, if and only if you play the same game as with Berling density. You pick a neighborhood of unity, you look at left shifts, you count the number of the intersection with gamma. If that remains bounded over all shifts, you call the set relatively separated. And then with this notion, you can essentially use pretty much the arguments that were in place for the abelian setup. And I should also say parts of this obviously are were known by Feichting and Gröchenig, so it's not entirely fair to fully put our names here. I think the interesting part is the second one. So if you have a frame of translates, then based on a set gamma, then gamma has to be relatively separated. And here's I think the novel part that is very much based on arguments for the abelian case. If G is non-discrete, then the set that you get by inverting each element in gamma, that gives you a new set gamma inverse that is not relatively separated. All right, and from this you can already conclude two things that are kind of interesting. The first one is if G is non-discrete, you can never expect to get a regular set of translates that gives a frame, so subgroups don't work. And if G is abelian and non-discrete, so this is essentially the generalization of the result by Deng, Christensen, and Chris Heil. If G is abelian non-discrete, there's never a frame of translates, because if in an abelian group, gamma is relatively separated if and only if gamma inverse is relatively separated. More generally, you can show that groups like the reduced Heisenberg group, which is essentially a quotient of the simply connected Heisenberg group by a discrete central subgroup, that does not admit a frame of translates. So that's an example of a non-abelian group, non-abelian, non-discrete group that does not have a frame of translates. Okay, and here is how I want to connect this to bandwidth. What does this have to do with bandwidth? So remember, if you have a subspace of L2 of G that has a convolution reproducing kernel, then the same set of, and suppose your group has a frame of translates, then the same set of translates can be used to construct a frame in every subspace that has a convolution reproducing kernel. And this is completely different than you would expect from the reals, because in the reals, what you expect is that if you remember, the discussion in the reals was convolution reproducing kernels correspond essentially to characteristic functions. And the bandwidth intuition there tells us that those sets of translates giving us a frame have to fulfill a density condition. So you cannot expect to get the same set of translates to work for all spaces, because the larger your omega gets, the denser gamma has to be. If you have a group that has a frame of translates, the same set of translates will work for all such spaces. So that's a huge difference between groups of with frames of translates and groups and the reals, for example. Now, all of this would be fairly interesting, fairly boring if there were no such groups, but there are groups that have frames of translates, and here's the first large class. Suppose the group is non-unimodular and of type 1. That's a particular representation theoretic condition that that has a fairly large number of examples we can choose from. Then G is has a frame of translates, and essentially the idea is the same as for the result I had for irregular sampling of sets omegas that are not subtiles. Sorry. Now I'm for some reason. Oh, sorry. I think I stopped my. Okay. Essentially, the same result by Freeman and Spiegel allows me to discretize continuous frames of translates that I know exist for these groups. And I will, in a second, exhibit one concrete group that's very useful here. And then there's a second result that's inspired by an argument by Iverson. Suppose you have a closed subgroup of a given group G that has a frame of translates, and that H has the additional property that its regular representation is equivalent to an infinite multiple of itself. Now, this looks, again, equally daunting as the type 1 condition, but it can be checked for a lot of groups. Then you can choose a set of translates inside the smaller group that will already give you a frame of translates in the larger group. There's a sketch of proof here that, again, I will have to skip. That proves the second theorem. And what I want to do is essentially now show the number of examples that we get of non-abelian groups that actually do have frames of translates in the regular representation. So the first example that springs to mind is the AX plus B group. The AX plus B group is a non-unimodular group. It is of type 1 because it is an exponential solvable group. Those groups are known to be type 1. Hence, it has a frame of translates. And also, if you decompose the regular representation, as people from wavelet analysis may know, you get essentially an infinite multiple of the same irreducible representation. And that infinite multiple is actually equivalent to an infinite multiple of a further infinite multiplicity. So the group G has a regular representation that's equivalent to an infinite multiple of itself. And what that entails is that every group that contains the AX plus B group as a closed subgroup has a frame of translates with translates that are concentrated just in that copy of the AX plus B group. So one concrete example, the group of 2 by 2 matrices with determinant 1, they have a copy of the AX plus B group inside themselves. So there's a frame of translates of the L2 space of the FSL2R that is made up of shifts that just belong to the subgroup and of a particular group of a particular generator in L2 of R. This generates, I mean, you can find copies of the AX plus B group in a lot of other groups, in SLNR, in SOPQ. In exponential solvable Lie groups that are not nilpotent, you find either a copy of the AX plus B group or of a second group that is non-unimodular type 1 and has this infinite multiple property. So you can show every exponential solvable Lie group that is not nilpotent has a frame of translates. Okay, so to summarize these results and to put them into the context of the previous parts of the talk, these are all groups where which completely contradict the bandwidth intuition, and it's mostly because of the X plus B group, to be honest. Okay, there are intriguing open cases here. So note again, we have exponential solvable Lie groups that are not nilpotent. For these, we know that they are FT. What we don't know is actually the class that leads up to that. So a non-abelian group that's simply connected nilpotent. Do they have frames of translates? Actually, we don't know that for the simplest example of these groups, namely the Heisenberg group. Right now, it's open whether the Heisenberg group has a frame of translates or not in its L2 space. My personal guess is no, but I really don't know. Okay, and at this point, I want to close my talk, and I thank you very much for your attention. And if there are questions, I'll be glad to answer them.
Thank you very much, Professor Führ. So there's a button everyone can press. At the bottom of your screen, you should see reactions. And then I have the option to clap or give a thumbs up. And it's an exclusive or, which is a shame. I want to do both. But okay, we have time for a few questions.